In this video, we're going to focus on gases. So previously we said that gases typically exhibit really weak dispersion forces. Now there are some other things about gases that have been noted over the years, and there's actually something called the kinetic molecular theory of gases, or KMT. So basically this theory just summarizes what we know about gases. So gases are composed of tiny particles that are separated by large distances. And again, that has to do with those dispersion forces. There just aren't enough strong interactions to keep those particles together. Now, gas particles are constantly moving, so they have a lot of energy, and that means they're going to experience collisions with other gas particles and the walls of their container. That's actually going to lead to a pressure within the container. The velocity or speed of gas particles is also related to the temperature of a gas. So if you increase the temperature of a gas, you should expect a higher velocity of gas particles, and you might experience more collisions between those gas particles. And then last, gas particles do not experience any force of attraction or repulsion with each other. Now, this isn't necessarily true because they do exhibit some dispersion forces with each other. But we're going to assume that they don't have any significant interactions with each other. Now, if a gas follows these statements perfectly, we call that an ideal gas. So again, if we looked at some gases, there are gases that exhibit exceptions to these descriptions. So not every gas is going to follow each of these descriptions exactly, but for the most part, this describes a gas. So let's talk about pressure a little bit more. So again, we said in the kinetic theory that gas particles can collide with each other as they're moving around. So off to the right, you can see that these gas particles are moving in several directions. So at some point, they're going to hit each other, kind of like billiard balls in a game of pool. But they can also hit the walls of a container and bounce off of that wall. Now, this is going to create a force, and that force divided by the area of the walls of the container yields a pressure. So pressure is something that we can measure for gases, but we don't usually consider pressure for solids or liquids. Of course, there's some exceptions to that, but typically we're just going to think about pressure for gases. Now, there are many different units of pressure, unfortunately. In chemistry, we typically use atmospheres or millimeters of mercury. Sometimes we'll use torr or Pascal, but most of the time we're going to just deal with these first two units. Now, the symbol for atmospheres is ATM, and atmospheric pressure, so the pressure that we feel from the air around us, is usually about 1 atmosphere. At least at sea level, and in Tacoma we're usually at sea level. Now, if you were in, let's say, Denver, which is a mile up from sea level, it's called the Mile High City, right? The pressure of the atmosphere is less. So if you've ever been to Denver, or if you've even climbed some mountains, you might have noticed feeling a little dizzy or a little weak, and that's because there isn't as much oxygen present, and it takes a while to acclimate to a lower pressure of oxygen. In fact, some people get what's called altitude sickness if they're too high up. Now, millimeters of mercury is given the symbol mmHg. So mm is for millimeters, and Hg is mercury. Now, if we want to equate millimeters of mercury to atmospheres, there are 760 millimeters of mercury for every 1 atmosphere. So we could easily convert between millimeters of mercury and atmospheres using that equality. Now again, there are several other units that we could use. For example, torr, that's just named after a physicist, and 760 torr are equal to 1 atmosphere, so that's really similar to millimeters of mercury. There's also pascals and bars, and then the last one, pounds per square inch, or PSI. You might have noticed that on the tires of a car, or even if you're trying to pump up a basketball or a soccer ball, the units on the pump might be in pounds per square inch. And there are 14.7 psi for every 1 atmosphere. All right, so let's use some of these units of pressure and do some conversions. So we'll do some practice here. So let's convert 4.5 atmospheres into the following units of pressure. All right, so for pascals, 1 atmosphere is equal to 101,326 pascals. So we can turn that into a conversion factor. For torr, 1 atmosphere is equal to 760 torr. And then the last one, pounds per square inch, 1 atmosphere is equal to 14.7 psi. So see if you can convert 4.5 atmospheres into the following units. So pause the video, try it on your own first, and then we'll go over it together. Okay, let's start with pascals. So remember, we always want to start our calculation with what we're given. And in this case, that's 4.5 atmospheres. And then we're going to multiply that by our conversion factor. So since we're trying to convert this into pascals, we're going to put this value on the top of our conversion factor, and then we'll divide by what we're canceling, which is 1 atmosphere. So the units of atmospheres cancels, and all we have to do is multiply 4.5 by 101,326. So when I plug that into my calculator, I get 455,967 pascals. Now, let's think about sig figs for a second. So in our given value, we only have 2 sig figs. So we probably want to limit our answer to the first 2 sig figs there. Now, the next value is a 5, so we need to also round up. So this would become 460,000 pascals. So pascals isn't the best unit because we get these really huge numbers. Atmospheres is probably the more desirable unit because we have smaller numbers, right? Okay, let's look at torr. So again, we're going to start with 4.5 atmospheres. And our conversion factor, we're trying to convert to torr, so we'll put that on the top, 760 torr, and we'll put 1 atmosphere in the denominator. So atmospheres will cancel and we'll end up with torr. So if we multiply 4.5 by 760, my calculator gave me 3,420 torr. Now again, we want to limit that to 2 sig figs. So it looks like the next digit is a 2, so we'll just round down. And this will be 3,400 torr. Okay, last but not least, pounds per square inch. So we'll start with what we're given. And again, we want to convert to PSI, so that will go in the numerator. And 1 atmosphere will go in the denominator. So atmospheres will cancel. And then when we multiply 4.5 by 14.7, we get 66.15 psi. And in order to limit this to 2 sig figs, it looks like we're going to round down because the next digit is a 1. So we get 66 psi. All right. So now that we've gotten a little bit of practice converting between units of pressure, let's talk about gas laws. So over the centuries, different experiments have shown that there are several properties of a gas that can be related to each other under certain conditions. So we can relate pressure, volume, temperature, and the amount of gas to each other. So pressure is usually given the symbol capital P, volume is given the symbol capital V, temperature is capital T, and notice that this has to be in units of Kelvin. And we'll talk about why later. And then the amount of material is usually expressed in moles, and that's given the symbol lowercase n. So there are several laws that demonstrate these different relationships. We've got Boyle's law, Charles's law, the combined gas law, the ideal gas law, Dalton's law of partial pressures, and Henry's law. So I did include slides on Henry's law, but we're not going to go over it, so I won't test you on that. But we will go over the other laws. So let's start with the first two, Boyle's law and Charles's law. So Boyle's law is a relationship between pressure of a gas and its volume. So capital P and capital V. Now, down below we can see an experiment where we have a gas in a chamber and the lid can move up and down. So let's say that the lid moves up. As we increase the volume of the container, so we have increased volume, we actually find that the pressure of the gas decreases. Now, if we moved that lid back down, we're going to decrease the volume and increase the pressure. And that makes sense, right? Because as we increase the volume on the right, the gas molecules are still moving around, but they have more room, so they might not hit each other as often. So with fewer collisions, we get a lower pressure. But once we decrease the volume, those gas particles are moving around and they have less room. So they're going to hit each other more often, they're going to hit the walls of the container more often, and that's going to increase the pressure of the gas. So what we find is that pressure is proportional to 1 over volume. So this symbol up here means proportional to. So actually, pressure and volume are inversely proportional. As one goes up, the other goes down. So this brings us to our gas law in this box here. So what we can do is take the pressure of the gas in situation 1 and multiply it by the volume of the gas in situation 1. And that's going to equal the pressure times the volume of the gas in situation 2. So that's kind of cool that those are equal to each other. They equal a constant. So let's do a practice problem. So let's say a sample of gas has an initial volume of 1.5 liters. So that would be V1. That's our initial volume of 1.5 liters. And it has an initial pressure of 0.87 atmospheres. So that would be P1. And then we're asked, what is the final pressure if the volume is reduced to 1 liter? Okay, so we're told that we don't know the final pressure, P2, but we do know that the final volume, V2, is 1 liter. And then we're going to assume that the temperature and the amount of the gas is constant, so we don't have to worry about those variables. So again, the law that we saw earlier is P1 times V1 is equal to P2 times V2. So let's plug our values into that equation. All right, so our initial pressure is 0.87 atmospheres, and we're going to multiply that by V1, which is 1.5 liters, and then that is equal to P2. We don't know what that is yet, so we'll just leave it as a variable, and we'll multiply that by V2, which is 1 liter. Okay. So now we're going to solve for P2. So how can we isolate P2 on the right-hand side? How do we get rid of that 1 liter? Well, we can divide both sides by 1 liter. And that way, 1 liter will cancel on the right-hand side. And we'll just be left with P2. So P2 is equal to 0.87 atmospheres times 1.5 liters divided by 1 liter. So now we can cancel units. We can cancel the unit of liters, and we're left with the unit of atmospheres, which is perfect because we're trying to solve for pressure. So this is a unit of pressure. All right, so all we have to do is multiply 0.87 by 1.5 and divide by 1. So when I put that into my calculator, I get 1.305 atmospheres. But looking at all of my given values, I have 2 sig figs in each of my given values. So let's limit this to 2 sig figs. So this will be 1.3 atmospheres. Now, let's double check if that makes sense, because earlier we said that if the volume increases, pressure decreases, and if volume decreases, pressure increases. So they do the opposite of each other. So in this problem, we were told that the volume is reduced. So the volume decreased. So we want to make sure that the pressure increased as a result. So our initial pressure was 0.87, and then our final pressure was 1.3. So yes, the pressure did increase, which is good. So let's just kind of write that down. So the volume decreased and the pressure increased. And that's what we expected to happen. Okay, so now I'm going to give you a problem to solve. So if a sample of gas has an initial volume of 0.56 liters and an initial pressure of 0.93 atmospheres, what is the final volume if the pressure decreases to 653.6 millimeters of mercury? So one thing to notice, the units of pressure are different. So you might have to do a conversion in order for your units to cancel properly. So remember, 1 atmosphere is equal to 760 millimeters of mercury. Okay, so see if you can do this problem on your own. And again, I recommend doing it the way I did it, where you list out each of your variables and what they equal, and then you can plug everything into your equation. So pause the video, try it on your own, and then we'll go over it together. Okay, so again, the law that we're using, P1 times V1 equals P2 times V2. Let's list out all of those variables. So we're told the initial volume is 0.56 liters. Oh, that's V1, not P1. So V1 is equal to 0.56 liters, and the initial pressure is 0.93 atmospheres. And then we're asked, what is the final volume? So we don't know what V2 is, but we're told that the pressure is going to decrease to 653.6 millimeters of mercury. Okay, so I'm going to do my pressure conversion first. And I think I'm going to convert millimeters of mercury to atmospheres. So let's do that first. So I'm just going to multiply this pressure by 1 atmosphere and then divide by 760 millimeters of mercury. So that was our conversion factor from earlier. So this actually gives me a value of 0.86 atmospheres. Okay. So again, the reason I did that is so my units will actually cancel when I set up my equation. Okay, so now let's plug in our values for P1 V1 equals P2 V2. So we've got 0.93 atmospheres, P1, times 0.56 liters, V1, and then P2 is 0.86 atmospheres, which we just solved for, and we'll multiply that by V2. Okay, so we're solving for V2, so we want to isolate that, and we're going to do what we did in the last problem. We're going to divide both sides by 0.86 atmospheres, and that way it will cancel on the right-hand side. Now also on the left-hand side, we can cancel our unit of atmospheres, and we're left with our unit of volume, which is liters. All right, so V2 is equal to 0.93 times 0.56 divided by 0.86, and our unit is liters. So when I plugged that in, I got 0.61 liters as my answer. Now again, we just want to double check that this makes sense. So we were told that the pressure was decreasing. So we would expect the volume to increase as a result. So our initial volume was 0.56 liters, and now our final volume is 0.61 liters. So it did go up. So that's a good sign. We did it right. Okay, so Boyle's law is applicable to our breathing, actually. So for air to move in and out of our lungs, the pressure inside of our lungs has to change. So that will force the lungs to change volume as well. Now we inhale about 0.5 to 1 liter of air per breath. And only about 1 to 2 torr of extra pressure is needed to exhale. So up above I have a diagram of that. So as we breathe in, the volume of our lungs is increasing. So the pressure of the gas in our lungs is decreasing. To breathe out, the volume of our lungs will decrease and the pressure of the gas will increase. So we're kind of forcing air to come in as we change the volume of our lungs, and then we change the volume of our lungs and force air out. So we're using Boyle's law every time that we breathe. All right, so let's look at that second gas law, Charles's law. So this gas law relates the volume of a gas to its temperature. And earlier I mentioned temperature must be in Kelvin. So that's why we learned about the unit of Kelvin in a previous chapter. So down below, let's look at our little diagram. In our first situation, we have a gas that's moving around at a particular temperature and it has a particular pressure. Now let's say we heat the gas. That's actually going to increase the volume of the gas. So we're trying to keep pressure the same in this case. So assume that pressure is the same and the amount of gas is the same. So in order to keep the pressure of the gas the same, we have to expand the space that it's in. So notice that the lid moved up. So as temperature increases, volume is also going to increase. And if temperature decreases, the volume will decrease as well. So that means that volume is proportional to temperature. So our gas law in this case, if we divide our initial volume by the initial temperature, that will equal a final volume over a final temperature. All right, so let's look at an example of how to use this equation. Let's say a gas has an initial temperature of 22 degrees Celsius and an initial volume of 1 liter. So let's write that out. So we've got a T1, an initial temperature of 22 degrees Celsius, and an initial volume V1 of 1 liter. If the temperature is increased to 30 degrees Celsius, what is the final volume? All right, so T2 is 30 degrees Celsius, and V2, we don't know what that is. Now, remember I said that temperature has to be in Kelvin. So we need to convert our degrees Celsius to Kelvin. So you might remember, in order to do that, we're going to add 273 to our degrees Celsius, and that will give us the value in Kelvin. Now, why do we need to do that? Why can't we just use Celsius? Well, notice that Charles's law has temperature in the denominator. Now, if we had a negative temperature, which in Celsius is possible, that would mess up our volume calculation. We'd end up with a potentially negative volume. So that doesn't make sense. But remember, Kelvin is a positive temperature scale. Every single temperature in Kelvin is positive. So we're never going to run into that issue if we use Kelvin. So we have to use Kelvin because the scale is positive. Okay, so let's convert our temperatures to Kelvin. So we're just going to add 273 to each of our temperatures here. So temperature 1 becomes 295 Kelvin. Temperature 2 becomes 303 Kelvin. All right, so next, let's plug our values into our equation. V1 over T1 equals V2 over T2. Okay, so let's see, we've got V1, which is 1 liter, and we're going to divide that by T1, which is 295 Kelvin, and that will be equal to V2, which we're going to solve for, over 303 Kelvin. Okay, so how do we isolate V2? So we can actually multiply both sides by 303 Kelvin. That way it's going to cancel on the right-hand side. And then that shows us that V2 is equal to 303 Kelvin times 1 liter over 295 Kelvin. So we can see that the unit of Kelvin will cancel and we'll be left with liters, which makes sense because we're solving for volume. All right, so all we need to do is multiply 303 by 1, so we just get 303, and then we'll divide by 295. So this gives us a value of 1.03 liters. Okay, so let's do one more practice problem for this video. Let's say that a gas has an initial volume of 0.54 liters and an initial temperature of 298 Kelvin. The volume is increased to 0.87 liters. What is the final temperature in Celsius? So we might have to convert our final temperature at the end. So see if you can do this problem on your own first. Pause the video, and then when you're done, unpause the video and we'll go over it together. Okay, so I'm going to list out everything that we were given. So we have an initial volume, V1, of 0.54 liters, and an initial temperature, T1, of 298 Kelvin. So I don't have to convert that temperature right now, it's in the correct units. And then the volume increases to 0.87 liters, so that's V2. And we're trying to figure out the final temperature, T2. Okay, now if we look at our equation, V1 over T1 equals V2 over T2, we need to isolate T2 eventually. So maybe we should rearrange our equation in order to solve for T2. Well, what we could do, let's multiply both sides by T2. That way we can get that value into the numerator. So that's going to cancel on the right. So if T2 times V1 over T1 equals V2, what can we do to isolate T2? Well, we could multiply both sides by the reciprocal of V1 over T1. So let's multiply, oh, I'm kind of running out of space, but let's see, we're going to multiply the left side by T1 over V1 and the right-hand side by T1 over V1. Okay, so that will cancel T1 and V1 on the left-hand side, so that we're left with T2. So overall, T2 is equal to V2 times T1 over V1. So kind of difficult. You can also just plug the values into your equation and then kind of go from there if that's easier for you. But it's always good just to practice our algebra, right? Rearranging equations. So let's plug our values in. So we've got V2 is 0.87 liters, T1 is 298 Kelvin, and then we're dividing by V1, which is 0.54 liters. So liters will cancel, and we'll be left with Kelvin. And if we plug this into our calculators, we get 480 Kelvin. Okay, so remember, we need our temperature to be in Celsius. So instead of adding 273, we want to subtract 273. So let's plug in 480 minus 273. So that will give us, let's see, 207 degrees Celsius. Okay. So hopefully that all made sense. We'll talk about some more gas laws in the next video, and we'll get lots of practice with these different gas laws. So I will see you then.